Hello, everyone. In this lecture, we will try to cover the greedy algorithms. So for the greedy algorithms, I would like to start with an example. So let's assume you would like to pay 37 cents, okay, 37 cents with the US denominations 1, 5, 10, and 25. What would you do? So the first step would be most probably, okay, so you will see that so there is 125 and the 37, so let me just give one of them, and then what will be left is 12 cents, right? For the 12 is greater than 10, then I can make it with a 10, right? And what is left is 2, so that means 2 cents will cover it, right? So by using 1, 2 plus 2, 4 denominations, you cover the 37 cents. Could you do something better? Not in this case, right? So, and the approach that we have taken while solving this problem is a good example of a greedy algorithm. Because at each step, what we did is first we took a feasible step, right? So whatever we do, it is valid. And the second is, it is locally optimal. So when I am paying 25 through 37 cents, by the way, my aim is to pay this amount with the least number of denominations. So I'm using just one denomination, that is the largest one. So locally, I'm making an optimal decision. On the other hand, whenever I take a move, it is irrevocable. So that means I cannot take it back. So that is a greedy algorithm. I am trying to solve an optimization problem. And at each step, what I do is I take a decision, and this decision is a locally optimal one. I do not worry about what will happen in the future, okay? But I do whatever I can do at best. That makes greedy algorithms very simple. And interestingly, sometimes they provide us the optimum solution. Not always, but sometimes they provide us the optimum solution. Okay, so mostly in this lecture, what I will try to do is I will try to cover some famous, renowned graph algorithms. Okay. And what are they? These are the minimum spanning tree algorithms by Prims and Kruskals, and then we will also cover the Dijkstra's shortest path. All of these algorithms provide us the optimum solution with a greedy approach. So let me start with the minimum spanning tree. So what's a minimum spanning tree? So we are given a graph. This is an undirected and weighted graph. And we would like to construct a tree out of that graph that will contain all the vertices in this graph. However, when I sum the edge weights, it will be the minimum. Notice that I am trying to create a tree from a graph. So that means, so let's remember what is the difference between a tree and a graph. In the tree, we are not allowed to have any cycles, right? So that means when I create a tree from a graph, there are no cycles in that. If I run a breadth first or depth first traversal on this graph, remember that we have covered this in our previous lectures, that will provide us a tree. Remember when you have the breadth first or depth first graph traversal, so that provides us a tree. This is a spanning tree. Spanning means it covers all of the edges. It is a spanning tree. However, those breadth first or depth first trees, they do not guarantee us the minimal cost. And now we are curious about that minimal cost. I like this example to explain the minimum spanning trees, so I will repeat it here. So let's assume we have a city. Okay, so this is a city, and in the city there are sites, houses. Okay, and these houses are all connected by roads. The new mayor wants to renew the roads because they are not in good shape. So let's say these are the muddy roads, and the mayor wants to renew them. However, renewing all the roads, in this example, you see the roads correspond to edges, okay? So it will be very costly because each edge has a corresponding cost of renewal. But the aim is to connect all of those sites in the city with a nice new road. So that brings the question. I would like to select the edges that will cover all of the vertices. From any of these vertices in this graph, I can go to another one by using the new roads. But I would like to minimize the cost. So that is exactly what I need to do with the minimum spanning tree. So as the mayor, you hire a CS guy, and that guy will provide you the minimum spanning tree of the roads with the minimal cost. So you see, so if you just make these black ones the new roads, okay, then the cost will be minimum. And from any site, you can go to any other by following these roads. Why? Because this is a tree. This is a spanning tree. And this is a spanning tree with the minimal cost. So we call this the minimum spanning tree. And how I can do this? There are two fundamental algorithms for the minimum spanning tree, and both of them are optimal. So we will start with the Prim's algorithm. Prim's algorithm actually follows an observation. And what is this observation? It tells that, okay, so let me just split the vertices into two sets. So I'm given a graph, and in this graph, I say that, okay, so vertex 1, vertex 3, vertex 5 is here. Okay, so and then the vertices, let me say V2, V6, V7, I don't know, V4 are here. Okay, so these are two disjoint vertices sets. Okay. And there are bridging edges between these two sets, okay? The observation tells us that if that is the case, then the minimum spanning tree should include the minimum cost bridging edge here, okay? Let me repeat it again. So you have some number of vertices here in set 1, and you have some others in set 2. And there are edges connecting vertices in set 1 with the vertices in set 2. Among these bridging edges, the minimum weight, the minimum cost edge should be in the minimum spanning tree. In the first glance, it's not easy to see why this observation holds. And let's assume it doesn't hold, and we will come to a contradiction. So this will prove us that this observation is correct. So here in the second figure, you see that, okay, so these are the vertices in set 1 and the rest. So these are the vertices in set 2, okay? So let's assume this one is your minimum weight edge. And you say that, okay, I'm not including this one, okay, but I will be including another one. And you know that the weight of this edge, so let me say X, if that is Y, X is less than Y. I know it because that's the minimum weight edge. But I insist, I say that, okay, so this minimum weight edge is not in the spanning tree. So I get this out and come up with another spanning tree. So once I come up with this other spanning tree, actually what happens if I insert the edge that I skipped in during the construction? So this will create a cycle, right? Why? Because in the minimum spanning tree, I have all the vertices in the tree, And if I put an extra one edge, this will surely create a cycle. And this is the cycle in my case, okay? But remember, once I insert this one, so there is a cycle, so I need to go and remove one of the others to make this a 3. And I know that the cost of this one is less than this guy. So let me just remove this one and insert this. What will happen? I will come up with a new spanning tree whose cost is less than the previous one. So that is why actually the observation is correct. And if you just split the vertices into 2 subsets, okay, and you should always select the minimum edge connecting these 2 vertices. So that gives us a good idea about the starting the minimum spanning tree. So let me just start only one of those vertices in set 1, okay, and I will put all the others in set 2. Randomly, that's a randomly selected vertex from my graph, okay? And this guy is connected to some others. What I will do is I will go and pick the one with the minimum weight, and I will carry this new guy to set 1. Now, I know that my starting vertex is connected with this new guy, with this minimum edge. And now, surely once this guy moves to set 1, it is connections with the set 2 are added to the bridging edges. Again, I will do the same thing, okay? So surely I have an example for this one. And first I would like to make the example, and then I will show you the complexity and other things. Okay. So let's assume I would like to start with only A here, okay? And I will have B, C, D, E, and F here, okay? Is there an edge between A and B? Yes, there is, and its cost is 3, right? And there is an edge from A to F, and its cost is 5, and there is an edge from A to E, right? And then A to E, so that is 6. These are the only bridging edges between my first set, let me say set 1 and set 2. Since this is the case, according to my observation, I should select the edge connecting A to B with the cost 3, because 3 is less than 6 and 5, right? Okay, then this is an edge in my minimum spanning tree, and that moves B into set 1. Okay, so let me try to make this. Okay, now B is here. Okay, so B is moved to here. I delete B from here, and A and B, they are connected with length 3. Okay, since now B is here, new bridging edges will join the connections, right? So B is connected to C with 1. B is connected to F with 4, right? And do I have anything else? As far as I see, I don't. Okay. Now the bridging edges. Okay, so A is connected to F and E. B, the connection between A and B, it's not being counted anymore because it's removed, because A and B are in the same set now. It's not a bridging edge. And I have 1 and 4. Among these guys, surely 1 is the least one, right? So that means I will include this guy, and this is in my minimum spanning tree. So let me do this. Okay. Yeah. Now I have C removed from here. Sorry. I have C removed from here, and now C is here. Okay, so, and B is connected to C, which one? Okay, then I keep going on. Okay, so A, B, C, these are A, B, C, these are my set one. So what are the bridging edges? You see 5, 4, 4, 6, and 6, these are bridging edges. Among these bridging edges, I see that the mean cost is 4, right? And I have two candidates for this one. Okay, so I can include B to F, or I can include C to F. It doesn't matter, because a graph may have more than one spanning tree, but the minimum spanning tree cost will be equal on all of them. Okay, so let's say I choose this one. Okay, so from C to F. I say that, okay, C to F, so that is 4, and I choose it. Okay, let me draw my spanning tree. A, B, C. From A to B, I have 3, so B to C, I have 1, right? From C to F, now I have 4. So F is my set 1, and in set 2, I have only what? I have only E and D. Okay. And now, what are the new bridging edges? Okay, so the new bridging edges, now that 2 comes into play. So, and that 5 is also into play. Okay, so I have 5, 5, 6, 2, and 6. Surely the least one is 2, so that makes E joining the game. F is connected to E with cost 2, right? And once I have it, what else I have? Now 8 becomes a bridging edge, but among these bridging edges, 5, this one is the least one, so I connect F with D. So that means F connected with D with 5 is another one. And I am done, because I have A, B, C, D, E, and F. All of them are covered, right? And what is the total cost? 3 plus 1 plus 4 plus 2 plus 5. This is the minimum spanning tree. Okay, so this is the Prim's algorithm. Okay. What would happen if I did not start with A, but let me say I start with F? Okay. Please try to do this on your own, okay? And you will see that at the end, the total minimum cost will not change. Okay, so maybe you might have different edges in your tree, okay, but the minimum cost will never change. Okay, so that is the Prim's algorithm. If you would like to implement the Prim's algorithm, so here is the pseudocode of it. And surely when we design an algorithm, its complexity is also important. So you observe that what I did is I split the, I always maintain two sets of vertices. And I need those edges, and I need to select the minimum weight bridging edge. Remember our discussions about the heap data structure. Whenever I hear something that at each step, I make a selection of the minimum or maximum, that makes me remember the heap data structure. Okay, so that means it would be nice to use a heap data structure here. Okay, so here is the data structure that is recommended if you implement a Prim's algorithm. I will be representing the graph as an adjacency list, okay? Remember, with the adjacency list, every vertex, for instance, so let me say A has a list of neighbors. A is connected to B, right? A is connected to F, and A is connected to E. And A is connected to B with a cost of 3, and it's connected to F with a cost, it's not connected, yes, connected to F with a cost of 5, not 2, okay, and it's connected to E with a cost of 6, okay, and I have all the other vertices here. So this is the adjacency list representation, and I will create a min heap data structure. With this min heap data structure, it will contain all the vertices, so A, B, C, D, E, and F. And each vertex should have a priority. And the priority is the minimum connection weight. For instance, for node A, its priority is 3, right? And for node, let me say F, its priority will be 2, something like that, okay? And then you will be maintaining this heap data structure, and that's a priority queue. So whenever we would like to continue this construction, what will happen is, okay, initially I will start with that V sub t represents the minimum spanning tree, no, the set 1, and I initiate set 1 with some randomly selected V0, and all the others are in set 2, and I have my priority queue. Okay, so once I have this, in this priority queue, I remove the initial vertex. I remove it. Okay, and then once I remove this initial vertex, what I do, I'm left with the others, and I should find a bridging one, right? So I start running this for loop, because at each step, I will move one of these vertices from set 2 to set 1, okay? But which vertex should I choose? I should choose the one which has the minimum edge weight connecting with the elements in S1, okay? So I run this one. So that is actually going to my minimum, my min heap data structure, finding the minimum guy, the one with the highest priority, but I'm not done. Maybe this guy has a minimum weight edge, but this edge is not a bridging edge. So that means whenever I pick the minimum guy from this heap, I should check whether its priority is correct. Its priority would be correct if that priority represents a connection, a bridging connection. If it is not a bridging connection, then it is not correct, and it should be updated. Okay, so you came to a vertex V, so it says that, okay, so I have a very good minimum connection with another vertex U, but if V and U, they are already in this set 1, this priority is not correct, so you update it, and you go to the next one. So and you update the priority according to this. There will be something happening in your tree, an update operation. And the moral of the story, if I run this algorithm, what will happen is, from the min heap data structure that includes all the vertices, so the size is V, okay, and I will need to remove one of them at each step, so this will bring that much of complexity. However, while removing, I should also check whether the priority is correct. So that means in the worst case, I may need to have the number of edges in the tree times update operations. So that is log V, right? And then if you just sum these things up, so you come up with something like n plus m times log n. Okay, so n is the number of vertices, okay? And with some further simplification, since this is a connected graph, so number of vertices should be less than the number of edges, and then it turns out to be that much, okay? Okay, so far, so good. So that is the Prim's algorithm. And there is one more. Okay, so the next one is the Kruskal's algorithm. The main difference is with the Prim's algorithm, what we did is we started with an initial vertex and created our minimum spanning tree one by one. First, there's only one node in your minimum spanning tree. Then you make it 2. Then you make it 3. Then you make it 4 up until you reach n. With the Kruskal's algorithm, it is the reverse. So Kruskal says that, okay, I will start with n different trees. N different tree means each vertex will be assumed a tree. And then I will merge these trees. Okay, so I will start with, I will start by, well, I'm not able to write here. Oh, it's here. Okay, so I will start with from 1 to n trees, and then I will pick one of those two guys. Okay, and then I will just merge them. Okay, once I merge it, I'm left with n minus 1 guys. I will pick 2 of them and I will merge them. Okay, until I reach a single one. This will be best understood with an example for sure. So let's do the same thing with the Kruskal's algorithm. Okay, so first, let me just make this a bit large. Okay. Now, I start the algorithm. So I have all of these edges and all of these vertices, and I assume that these are all individual trees of size 1. I would like to find the connection, the minimum connection between these trees. So that means I need to find the minimum edge, right? So once I find the minimum edge, it is 1, right? Now that means that B and C is connected. Okay, so they are in a cloud, and this is the connection. Now I'm curious about the edges connecting all the remaining guys, okay? And I have 3 here, I have 5 here, 6 here, whatever. And I see that, okay, so there is 2. So that is the minimum one. That means this will be another connection. So let me try to write it here. So now B and C, they're connected with 1, and you make it a set, right? And now I have F and E, which are connected by an edge of weight 2, and they are connected. Okay, now I'm curious about, and what else I have. So I have A here and D here, so these are just standalone guys. I'm considering how I can just how I can bridge BC with A. So BC with A, it comes with a cost of 3, right? So this connection, the minimum one, is equal to 3. How I can connect FE with the others? Okay, so let me finish the BC part. Okay, so BC is connected to A with 3. BC is connected to D with a cost of 6, right? And BC is connected to FE with a cost of 4. I did the same thing. FE is connected with A with a cost of 5, right? And FE is connected to D with a cost of 5. And is there a connection between A and D? No, there is nothing. So among these guys, what is the minimum one? It is BC connecting to A. Now that means, okay, so I have B, C, and A forming a tree. B, C is connected by 1, and this one is connected to A. So what is the connection? So it is the BA, right? So BA is connected with this one just with 3, okay? Yeah, BC is with 1, BA with 3. Now I am done, okay. And I have the FE here, okay? And then I have the D there, okay. Now I will consider, let me get these ones out and make it more concrete now, okay. So what I have so far selected, I have selected this one, right? And this one is also selected, and this one is also selected. Now, A, B, C is a set, right? F and E, that is a set, and there is D. So what are the connections between these guys? ABC is connected to FE with these connections, right? And the minimum one is 4, right? And FE is connected with D with this minimal connection, and ABC is connected with D with this minimal connection. Among these ones, 4 is the least, so that is why I will choose this 4. So let's see. Okay, by the way, you can choose FC or FB. Remember, it was the same with the Prim's algorithm. So I will be just connecting these two guys. So once I connect these two guys, now A, B, C, and FE, these are connected. Okay, so in F and E, there is 2. And so let's say I made a connection between F and C by 4, and this is done. And what remains? What remains is I will be adding D to this set, connecting D, and D is connected to this whole cloud with the score of 5 at minimum. You see, at the end, actually, you reach the same solution that you did with the Prim's algorithm. Okay, so this is how it works with the Kruskal's algorithm. But actually, although the pseudocode seems easier, seems more simple, let me say, when compared to the Prim's algorithm, running Kruskal's algorithm requires more sophisticated data structures. You know why? Because whenever you combine these two sets, you make a union, okay? And then once you make this union, you should make sure whether your next minimum edge is something between this union data, between this union vertices and the remaining guys. Okay, so that test, that verification is not easy, and it requires a union find data structure. Okay, union find data structure is something like, so actually I will be covering this in more detail later. Okay, so you have a universal set, and this set is split into some subsets. With the union, you will select one element from here, one element from here, and once you would like to combine these sets through these representatives, all of the elements here and all of the elements here, so they will become a set. Okay, and surely whenever you query an element, you would like to find which set contains this element, and this is done with the union find data structure. But again, by using a union find data structure plus a min heap, we will have this complexity with the Kruskal's algorithm. Very competitive to Prim's, but again, Kruskal's algorithm requires this union find data structure for efficient implementation, which we will discuss later. Okay. Okay, so up to this point, we have seen the Prim's and Kruskal's algorithms for the minimum spanning tree. And at each step of those algorithms, what we do is we just take the locally optimal step. We do not think, we do not spend time to analyze what will happen in the future. We just pick the most appropriate one. And interestingly, both of them provides us the optimum solution. Here is another graph algorithm that provides us the optimum solution with the greedy approach, and that is the Dijkstra's shortest path algorithm. Recently, there appeared another algorithm that beats this Dijkstra's shortest path. Maybe in the upcoming years, we will need to cover that one, but this is a good example. This is a good example of the greedy algorithms. And initially, when you look at that, okay, so it is not, again, easy to see why it works with just a simple step, okay? So let's see, okay. What is the goal? The goal is I am given a graph. So assume I'm given this graph. I'm given this graph. What I want to do is I will start from a given vertex, okay? So that is a single source. I say that, okay, so I will start from, let me say, I will start from C. And when I run the algorithm, I will have the shortest path from C to all others. Shortest path means from C, how can I go to A? So let's see. From C to A, I can follow this path, right? So 5 plus 7. So that will make it 12, okay? What else? I can go to E and then D and then A. Oh, okay, so that's 6 plus 4 plus 7, so that is 17, okay? It seems CDA is better than the other one. What else? From C to D, D to B, B to A, 5 plus 2 plus 3, so that seems even better, right? So it is now 10. And you see, there can be some others as well, okay? Among these possibilities, my algorithm, the Dijkstra's algorithm, will provide us the minimum cost. Minimum cost starting from the single source, from an initial vertex to all of the others. But the important point before discussing further details, we assume that each edge has a non-negative weight, okay? If the edge values are negative, so this will have some difficulties, and you will see why, okay? Let's assume I have an array. This is the array of D. Okay, so I have an array D. And this D array is of size number of vertices. Okay. It is something like that. Okay, so DU is the shortest distance from starting vertex S is my starting vertex, to the vertex U. Okay, that means I have here DA. Okay, so that is DB. Let me say DC, DT, and DE. Initially, what I do is I just make them all infinite, except the starting one. So let me say I'm starting with A, and I make it 0. Okay. Okay, so it's this one. This is my starting vertex. What will happen at each step is, so I will check and I will try to find the connections, okay? So at each step of this iteration, I will be choosing the smallest du, okay? And then I will update the connecting neighbors. So what it means, so I have those values. Initially, I have a is equal to 0, and all the others are equal to infinity. What is the minimum of this? Again, remember, I will be always asking for the minimum, so that makes me remember the heap data structure. So let's assume I have a mean heap data structure constructed over all the vertices, okay? And what is the minimum? So minimum is this one, right? Okay, so since minimum is this one, and this one is connected to the other two guys, I will go and update the corresponding distances. I say that, okay, so I can arrive to A with cost 0, and I can arrive to B with a cost of infinity. However, A is connected to B with 3, right? So then the cost of dA plus 3 will be feasible to reach dB. And 3 is less than infinity. So let me update this to 3, okay? Similarly, from A to D, I can come with a cost of 7. So 0 plus 7 is equal to 7, and 7 is less than infinity. So that is why I make this 7. You see, now what it tells that, okay, so you're starting from vertex A. It has a cost of 0 for sure. And from A, you can go to B with a cost of 3, and you can go from A to D with a cost of 7. How about the remaining guys, C and E? I haven't touched them, so that is why they are still infinity. Okay. Next, among those D values, I will pick the smallest one that has not been selected before. Once you select this one as the minimum, you should remove this from the minimum heap, and you say that, okay, so I started from A, and now I'm not able to choose the A again, okay? And from the ones, I have 3, I have 7, I have infinity, and I have infinity. What I will do, I will pick the next smallest one. It is B, okay? Now from B, I have new connections. From B, I can go to C with a cost of 4. So arriving C was previously infinity. Now 3 plus 4 is equal to 7. 7 is better than infinity, so I will make it 7. What else? B is connected to D. And B has a cost of 3 plus 2. It makes 5 to reach D from A by following the path AB and BD. So that makes the cost of D, not 7, updates it to 5. Okay. Good. Now I have these ones, and what I will choose, so there is 7 here, there is 5 here. So 5 is better, right? So then I will take this path, okay? And I will do the necessary updates again with the next steps. Okay, so this is called the edge relaxation. I will repeat it again. So once you have those D array and you choose the smallest one, so whenever you choose the minimum one, you update all the other D values that are connected to the selected vertex. This is called the edge relaxation. If this update provides you a better value, you delete the previous value and make it the new smaller one, else you do not touch it. Okay, so that is the Dijkstra's shortest path algorithm, and here actually we covered it almost all, but let's see what the book also suggests. Okay, initially everything is infinity other than A. You start with A. Okay, so from A, you take the minimum one, BA3, so this one is your minimum path to B from A to B. And then what you have here is D, you update the corresponding values and then you choose. Okay, so this one is your next value. So you first choose this one and then this one, okay? And then you add this guy. Okay, so that is 2, right? And you see this one is added. And then the next best is accordingly C. So that makes this connection, okay? And then you have this one selected. And once you have it, so the next guy will be this connection, okay? Now you have all the costs starting from A, reaching to B, its cost is 3, okay? From A to D, it is 5, right? So from A to C, it is 4 plus 3, so that is equal to 7. From A to E, so that is 3 plus 2 plus 3 plus 2 plus 4, so that is 9, okay? And this is your final allocations. Okay. As a summary, when you run the Dijkstra's shortest path algorithm, that the pseudocode is here, you find the shortest distance starting from an initial vertex to all others. Besides the value of this, besides the cost of this path, you also have what this path is with the data structure you use here. Okay. Again, you make use of a mean heap data structure. It is really easy. You initialize a priority queue, right? And this priority queue, the initial one has the priority of 0 and all the others have the priority of plus infinity. You pick the smallest one. Once you get the smallest one, you perform the edge relaxation and update the priorities of the other nodes. You again go and pick the minimum one and update the priorities. You pick the one and update the priorities. Same story. The size of the heap is initially equal to the number of vertices V. So that means you will need to have V times log V removal operations until you cover everything, okay? But at every step, you will be updating the weights, updating the distance array, okay? And updating those priorities can be as much as the number of edges in this graph. And that brings another cost of E times log V. So in total, you have that much complexity. Again, we assume that we are representing our graph with an adjacency list. Okay. So that is the shortest path algorithm. And that concludes our lecture about the greedy algorithms. So we will have some more examples in the classroom. But we should be all very fluent on computing the minimum spanning tree of a given graph by the Prim's algorithm, by the Kruskal's algorithm. So these two are for the minimum spanning tree. And what else? I should also know how to run the Dijkstra's shortest path, okay? And Dijkstra's shortest path is a single source shortest path solution. You start from an initial vertex S and you find the shortest path connecting S to all other vertices, all of them, while running the Dijkstra's algorithm. You know the complexities and the mean heap data structure and the adjacency list representation. What is missing is the union find data structure in the Kruskal's algorithm that we will try to cover later. Okay, thank you so much. and take care.